In 12, what we want to do is justify that the algorithm requires n-square floating point operations, and this algorithm solves the system ux is equal to b, where u is upper triangular and x overwrites the vector b. So if we look at this, the updates are done in this region, and notice what's happening here. Beta 1 is updated by taking beta 1 and dividing by nu 1, 1. Well, this is just a scalar. It's only requiring one floating point operation every time we do an iteration. On the other hand, beta b sub 0, which is a vector, is updated by taking b sub 0 minus beta 1 times u sub 0, 1, which again is another vector. And so what we need to do is figure out how many floating operations are required for this update. Notice that on the kth iteration, the size of b sub 0. Well, in the beginning, b bottom has 0 rows, so b top is everything. And b top is partitioned into b sub 0, beta 1. So for the first iteration, the size of b sub 0 is n minus 1. After the kth iteration, once we slide through, the size of b sub 0 is going to be n minus k minus 1. And so that's actually the same size as u sub 0, 1, which means that this part of our problem is actually going to take n minus k minus 1 multiplications, because we're multiplying every one of the entries in u sub 0, 1 by this scalar beta 1. So this will require n minus k minus 1 floating point operations, and then the update for b0 requires another n minus k minus 1 operations. So this command here at each iteration is going to be 2 times n minus k minus 1 floating point operations, since the size of b0 is n minus k minus 1. This is true for every one of the iterations, and that would mean where k ranges from 0 to n minus 1. So the total number of floating point operations will be the sum k from 0 to n minus 1 of 2 times n minus k minus 1. What I'm going to do is a substitution. I'm going to let I be equal to n minus k minus 1, and that would mean that I ranges from n minus 1 to 0, and the sum, this sum is equivalent to the sum from I from 0 to n minus 1 of 2i. And this is just 2 times the sum I equals 0 to n minus 1 of 2 times I. Notice I sort of ignored this one floating point operation because it wasn't really adding very much to the total sum. And notice in this particular case, this becomes, I already I factored out the 2. So this sum is actually 2 times n minus 1 times n divided by 2. We ran into this sum several times already, which means it's approximately n squared. And so it's actually n squared minus n, but we're going to have plus n because of these floating point operations. So it's pretty close to n squared floating point operations.